So, we will do molecular dynamics. So, this is one reference, there are many references, but I have just taken some material and some code from a website. I have modified it, but is general code. So, MD is you have lots of particles, okay. It could be million particles or even few million. Okay. These particles have mass Mi, these particles have mass Mi and position is Ri and force acting on the particle is Phi. Okay. So, Newton's law, right. So, mass times acceleration is force. I am not thinking of quantum mechanics right now, we just assume for this course classical. There are ways to solve quantum particles using Schrodinger equation, but that is beyond this course. Okay. And sometimes you do not get the force, but you get the gradient of a potential. So, you are given potential, you can find force. So, how do I solve it? So, this is in fact a second order differential equation for all the particles. They are kind of okay, they are connected by the potential, but I can solve all of them independently. Well, particle I will need to know where the particle j is, but you can solve all of them simultaneously. You need to compute f I, which may depend on the particle position of particle j. Okay. But that is not a problem. So, the formula which is this is straightforward formula. So, this acceleration, right. So, R I, so acceleration is R I t plus delta t minus 2 R I t plus R I t minus delta t, second order formula, by delta t squared. This is equal to force F at time t on particle I. Okay. I rewrite it, then I get this equation. So, this formula has one, well, it is a second order accelerate, but one disadvantage you may call that I need to store a position of time at time t as well as a previous time. So, this is at previous time, this is current time and this is future time. So, storage required is twice, well this second order accurate, but you can do in one shot. Of course, I could use a Rangakuta, given the current position I can compute next, but I need to store the midpoint as well. Okay. But okay, so you can choose whatever you like, but this one illustration from the book I took and is followed in many MD simulations. Okay. So, you just need to do this, and you can also get the velocity field from the position, right. The position is so the second order accurate and the velocity and this is kinetic energy plus potential energy. So, for this system the total energy must be conserved, okay. There is no friction, so it should be conserved. So, there are several types of problems people solve. So, this called one problem is called hard sphere interaction. So, we have these hard spheres, they are moving with velocities and they interact only when they collide. Okay. So, there is no potential, only the collision will give you the interaction. So, this problem has this issue, this problem is not easy to solve. No, actually it is easy to solve, but it is not very efficient, because you have to keep going until you hit a particle. Okay. So, there are issues with this when you implement in computer. It is a free particle until it hits, but we do not know when will it hit, and they do not hit simultaneously. When this guy hits, other guy is still moving. So, the interactions are very less and you spend a lot of time just moving with constant speed. So, this is not very suitable method for MD, and the formula this is the formula, okay. After the collision but you have to wait till the collision. So, you have to figure out when I am going to hit. So, keep going until you see the radius of this particle, then you apply this this formula. Anyway, this is not often used. So, one popular potential is called Lennard-Joule potential. Okay, you might have heard about this. Two particles which are far away, there is the interaction. It's a quantum mechanical fully. Okay, there's some electrodynamics, electromagnetism as well is involved, but anyway, this was derived by Lennard and Jones, and the force is given by this between two particles. So, what do I need to do? There are many particles. So, I need to pick a particle I or particle A. Well, my notation is differs slightly from formula I wrote in the previous slide. For particle A, it is interacting with all other particles. Okay. So, this particle B, particle C. So, the force will be for particle A will be for A and B, I need to say my delta R is R B minus R A vector, and this will go here. This for particle B. Similarly, you do for particle C. So, there will be a loop for particles. So, the algorithm involves for particle A for all particles outer loop, or for particle label, well, I mean for all particles you have to loop, no, particle 1, 2, 3, 4, and then for particle I, particle A, compute force on A, then time advance. Okay. So, but of course, you should store the position and for computing, like once I time advance it, the position of A is updated, but I already stored position of A somewhere, right. So, I should not use the updated position, then that will be a mess, no. So, you should use the position which is recorded and not the updated ones, because some are updated, some are not updated. Okay. So, we can use this algorithm, and if we solve, well, I am going to show you for some, not this potential, but for gravitation potential, one code. And so, it turns out if you have enough number of particles, you get this Gaussian distribution, sorry, this Maxwell distribution. Okay. So, these for different temperature. So, what is temperature? I can take n particles, and the average kinetic energy per particle is kBT. Okay. So, that is temperature. So, there are many codes, but I want you to write a program. Okay. So, we can compare with some codes, but let us write ourselves. This is quite easy to write. So, let us think of the project will involve, I mean I would recommend that you use either Lennard-Jones or gravitational interaction, but this problem is not solved. Lennard-Jones gives you Gaussian, no problem, but with gravitation it is not clear what the answer is. Well, why is only thinking of atomic particles? You can think of galaxy, right, or the universe, and all the galaxy, planets, stars are formed by gravitational interaction. Okay. So, we are thinking of universe, okay, or at least planet. So, think of n particles of unit mass. Let us keep life simple. So, particle A's position is R A. So, the F A will be this, right. So, sorry, M A is 1. No? So, it is a 1 by r squared force. So, I write 1 over r squared as this is a vector, no. So, r b minus r a, this one, correct. So, this force is mass times acceleration. So, m is 1. So, acceleration is this formula. well, subtract, I rewrote it, as I wrote in the last slide. So, this will give us updated position of the particle, fine. So, you need to compute total force on particle A. So, sum over all particles. So, this is a code we can use, this is basically C like. So, we can speed it up by Numba. So, in fact, the loop is obvious. So, this is a function n body NB is Numba. Okay. So, I am doing n steps is 5, but you need to do more in project. You should really do a long simulation. So, this is time loop. So, I do 5 time loops, and this for the particle loop, which I said for every particle I need to compute the updated position, and for particle j I compute the force and update. So, how do you compute the force? So, I have several variables called current position, POS is short form for position, pos current, pos previous and pos next. I have made one mistake here, okay, there is something missing here, I will tell you what. So, these are the 3 delta R's. This is a RB minus RA, correct. So, XYZ, this is a 3D simulation, and then this 1 by R cube, this 1 by R cube. Well, you need to first do the square. So, mod of this, square it. So, this is the formula, square, then this 1 over R cube, and force will be, for this is RB minus RA or delta divided by RB minus RA cube. This was single particle, but I need to add for all the particles. So, first set force to be 0, where this force is set to 0 for every particle, then loop and keep adding the force, and I will get the net force. Then I get the next position by the second order scheme, which I wrote in the previous slide. But here now I got the next position, then I go to the loop again, right. This for particle I, and then so this is going to be so this should be part of this. So, once every particle is updated, then I need to do one more step. What should I do before return? So, all the particles are updated to new position. Then what should be the current position? Updated one. So, I need to write pos. So, a loop, you write a loop, pos current equal to pos next. Okay, and pos previous. So, no, I think you should first put pos previous. Pos previous equal to pos current, and update pos current by pos previous, pos next. Okay, this needs to be updated, and then we go to the next loop for the next time loop. Okay, this of course this has to be in a loop. But I just wrote it in the vector form. Okay, but you can write the same code in a vectorized Python form, no problem. Apart from this error is there in the Google Colab, you will see that. So, of course, that was the function. Now, I can run it by, you can start with probably 100 particles. So, I initialize the current position by random positions. Previous positions are, you can set it to zeros. Okay. Actually, no, this is not a good idea. Previous should be like current. I would say that put this as current. In the initial condition, previous and current should be same. And pos next is 0, because next will be updated. But I believe previous pause prev, I am doing something like that here or no? Okay. Yeah, this is what is being done. Pause prev is pause current is being done there. Okay. So, it is good idea to keep the previous, because first time we do not know what is the position at t minus 1. So, this initial condition is always a problem for these are called n step method, no, multi step method. If you done the computational physics course, you may recall, like Adam-Bashforth is one such method. So, I need the position at previous time, but initial condition we do not have the previous time. So, that is a issue for such schemes. Anyway, after we set it up, then we can time step and you can find the total time. Okay. So, what is the challenge? The reason why I am interested in this problem is thermodynamics of gravitating system is not known. Well, there are theories, but not everybody is happy with those theories. Why? Because all the statmech theories you might have studied is for short range interactions, right, like particle interaction is when it collides. Lennard-Jones, though it is a long range force, well, it is a short range interaction. Lennard-Jones, if you look at the potential, is basically like this 0, V versus R. So, they interact only when the particle distances are very small, otherwise a free particle. Ising model, nearest neighbor interaction. So, long range interactions thermodynamics becomes a problem, partition function becomes very complicated. So, that is a issue. Now, I am also thinking in the following manner. So, the present system, in fact, I do not consider a heat bath at all. Okay. Thermodynamics is normally a heat bath. If not external heat bath, you think of the full set of particles as a heat bath, and one particle is in the influence of other particles. But let us not think like that. We just let us think that we have an isolated system of n particles. Now, what does the second law of thermodynamics say? In isolated system, so system should it become ordered with time or disordered with time? Disordered time. But what do you expect in a gravitating system? Do you expect it to make more disorder or more ordered with time? There will be clumping, and clumping is like ordered, right. So, it is an isolated system which may show more order with time. Okay. So, I think this is a problem which I am interested in. So, which can, well, so second law I would say that I am not happy with the statement that everything should go from order to disorder. Some things go from order to disorder, but not everything goes from order to disorder. Okay. If you are interested to read more, then you can read some of our papers. So, we did study a 2D hydrodynamic system called Euler equation. Okay. So, this is just a side, maybe I can just use the next slide, which is I think is empty, no, not empty. So, Euler equation, which is Navier-Stokes. Euler equation is this. No viscosity and no external forcing. In fact, this is a hydrodynamic description of a Boltzmann gas. So, if you look at coarse grained picture of all these particles, Lennard-Jones particles which are colliding and interacting. So, this is the equation you will get. You can derive it in fact from kinetic theory. Now, this system we find that with time, we start with some initial condition, with time we get very ordered structures like vortex or shear in 2D. Okay. So, this system is getting more, I mean, what happens to the second law? So, second law I would say that is, I agree that heat cannot flow from cold to hot, but making the statement about everything should become more disordered, that I think is not correct. Okay. So, we have concrete example here. We basically get shear structures like these, or so this is a physical review fluids 2022. You can just search and you will find this paper, which is easy to read, very easy to read, and we show that this indeed happens in 2D, not in 3D. Okay. You may say 2D is artificial, but that is a separate matter. 2D is not so artificial. There are examples of in Earth atmosphere can be treated as 2D, quasi 2D, and the cyclones are ordered structure, right. I mean, suddenly they appear. Of course, in a heat bath there is earth, there is a sun heating the earth. So, that is why we wanted to make an isolated system, that is why important. Do not connect it with a heat bath, keep it isolated and study the order. The problem, another problem is how to define entropy. So, entropy is defined from the partition function, right, in thermodynamics. But if I do not have a heat bath, so there is no beta or e to the minus beta E, no. So, then how do I define entropy? So, I hope I am not confusing you all, but there are some interesting questions which can be looked at, and this is one example. So, that is why I am interested in this example. That is my personal interest, but of course, you can just do it with interest or without interest, but this is a interesting computational physics problem by itself. So, we can take here, if you want periodic box you can take for this problem, okay, or you can think of reflecting wall, you can think of these particles sitting in the box. So, it is your choice. The reflecting is more realistic, but periodic is also fine. Okay. And large, I think 100,000 is large for you. If computer allows, then you can go to million, but 100,000 should be okay. So, what about the parallelization issues? So, I recommend that this group they can write a Python code and run it on a GPU. This will take time, these systems do take time. So, you can test it on a GPU, the code which I wrote should work. You do not need to write a new code, but you can test it out. By the way, I did not test the code, I just wrote that part by taking some clue from some other website. So, you can just test it and get started. So, convert it to GPU, like at least CUDA Python, which we will teach in the class, and run it for a long time. Okay. And one GPU should be enough for 100,000 particles. Okay. You can do MPI, of course, people who are interested can do MPI, but MPI is very complicated. Why MPI is complicated? So, particles are, imagine I want to divide this into two processors. Particles are moving randomly, no. Now, the particle which is a processor P0 can go to P1, and some P1 guy can go to P0. Now, how do I keep track? I have to keep track these particles when they are crossing the boundary. Okay, keeping track is not a problem, but these particles you are putting in an array, right. So, particle 0 is position and velocity is here. Position, which my algorithm I need only position. So, all these are here. Now, imagine particle 3 goes out to the next processor, then there is a hole, there is no particle here. Then how do I do in a loop? Something there is a hole and it is not, I mean vectorized loops become a problem, right. NUMBA will get confused, there is no particle there. So, that is the issue. So, the most sophisticated thing which can slow down the computer is using a list. You heard of list? Some of you may have done data structures. So, you can think of this as a list. In Python there is a list, right. So, you can throw any member of the list, but you may know that list is very slow compared to numpy arrays. Okay. So, that compromise you do not want to do. So, that is a big issue. So, I suggest that do not worry about this MPI simulation for this, just work with GPU and implement it. But I think of physics, think of large simulations, different initial condition, it should be an interesting project. I would say that indeed there is one strategy which is followed is that the particles are too far away, then you do not take into account, I mean you do not add the force by that particle by shielding. You say, well, it is too far away. So, there are strategies, but I think we can ignore it. Implementing those strategies are quite reasonably complex, but for time being ignore it. If you are interested, you can do it. In our lab there are people who are expert of this, so you can talk to them and you can implement. This is called KD tree. So, it looks for nearest neighbors and it computes, well, not nearest neighbors only, some neighbors within some radius r and ignores the rest. Okay. So, that is what I would say, that focus on a GPU, we need more particles, but we need a pretty long runs, and it is an interesting problem. Okay. So, we study Ising system for 2D, okay. That is what we will do. If you are more interested, you can try 3D, but I am showing you for 2D. So, these you need to compute magnetization. Well, we will focus on phase transition, okay. So, we know, so let us look at the system. Is there in some heat bath? So, it is in heat bath, okay. So, like you can think of magnet, Ising system is in this room. So, there is a temperature of the room. Now, this spins can be either all aligned in one direction, which is right now up. So, this is called ordered phase, or it could be all disordered, up down up down up down, and this is called disordered phase. Okay. It turns out if the temperature is cooled to some low temperature, then it does become ordered, and this is a critical temperature below which it remains ordered and above which it remains disordered. It is known this part, and interaction here is short range interaction. Okay. So, the Hamiltonian or energy function is minus j SI Sj, and the Ij are for the nearest neighbors. So, for this particle x, I compute the energy. So, I look at the 4 neighbors, not the diagonals, okay, only the face neighbors. So, there are 4 guys. So, down will give you 1, minus 1, right. This is we take value 1 or minus 1. So, 1 1 and there is a minus in front, and j. So, minus j, this will give you what? This together 1 and minus 1 gives you minus 1, but there is a minus sign. So, that gives you plus. So, this gives you plus, this gives you minus, this gives you plus, and this gives you plus. So, this is 3 minus 1 is 2j. I need to compute for all particles, but only neighboring interactions. Okay. This was pointed out by Ising. The model was constructed by Ising. It has become very popular. Now, the course project is how to get the phase to critical temperature. Okay. So, magnetization we need to compute for, I mean it is function of time. So, you will not get this in the in time t equals 0 or time any time, it will take long time to reach there, but you should know, am I going there or not, this state. So, magnetization formula is this m up minus m down divided by m up plus m down. If all of them are in one direction, then either plus 1 or minus 1, right. If all are up, then it is going to be plus 1, all are down is minus 1. If half plus half up half down, then 0. Okay. So, how do we solve this? So, for n spins, So, n is a 2D spin, okay. So, n is the total number. So, how many configurations we got? 2 to the power n configuration. In partition function, this is a partition function, okay. Now, I need to compute for 2 to the power n, I need to sum it up. Now, for n equal to 10 power 4, it is 10,000 particle, which is not too much. So, number of configuration will be 2 to the power 10,000, which is 10 to the power 3000. 2 to the power 10 is 10 cube, okay. So, it is huge, impossible, okay. I mean, you can't do it. So, there is a clever algorithm, okay, called Metropolis algorithm, okay. So, what does it do? So, imagine I have two configurations, alpha and beta. Okay. In fact, they change only by one spin. So, one spin is flipped. So, what is the difference in what is the ratio of probabilities? So, by using the both, this is a probability formula, okay. I am not going to derive this, but this is a part, everybody knows this, right? E power minus beta e, and to normalize it I need to divide by partition function. So, this probability will be E alpha minus E beta by k b t. So, if alpha is E alpha is lower than E beta, then what happens? So, this becomes negative, negative becomes positive. So, it is preferred, lower energy is preferred, no, that is why systems want to go to ground state, but because of temperature they keep getting kicked up. So, they can't remain in the ground state, okay. You want to take a rest, no, you have to, they keep getting thrown up, but okay. So, they keep going down. So, this matrix algorithm is, if your energy is lower, then go there. If it is not lower, if it in fact it turns out that E alpha may be greater than E beta, then go to the next state or high energy state with certain probabilities. So, that is the algorithm. So, if E beta is, did I make a mistake? If E alpha goes to beta, okay, yeah, alpha goes to beta, if beta is less than alpha. So, I was, so you go to lower energy state, which is E beta is lower than E alpha, but if E beta is greater than E alpha, then you go to the higher energy state with this probability. So, if beta is too much bigger than E alpha, then negligible probability, but in the neighborhood, then we allow it. Otherwise, mixing is not possible, I mean, then everything, if you do not allow this, it will just go to ground state, okay, which is unrealistic. So, this is the algorithm which is there in my book. So, start with some configuration, is energy. So, I am going to, so look, in StatMech partition function involves or computing memorization involves summing over all configurations, but here we do not want to sum over all configurations, there are too many. So, you say, well, let us look at some sampled ones. So, this algorithm is basically tells you that, okay, you focus on these steps or these configurations. So, start with some configuration, okay, which energy is E alpha, then randomly pick a site I j and flip its spin. So, you got a new configuration, its energy is E beta. If E beta is less than E alpha, accept the configuration, okay, that is the next configuration, and after that I will go to the next. Okay. If E beta is greater than E alpha, then accept the configuration with the probability this. So, you got the next configuration, after that repeat the loop. So, go to the next one. So, keep doing it until what? Your average magnetization saturates. Okay. So, saturation is okay, my system has basically reached an equilibrium. Okay. So, this is the code. First we need to initialize the array, is in Python. So, I again use this boundary, boundary. So, there is a boundary which I set to 0. We can try something else, but I felt 0 is like doesn't disturb the system, doesn't bring in new interaction energy. and so this is for initialization. So it turns out the random number generates either 0 and 1. This is a random int, but I want 1 and minus 1. Okay, so I have to use this if. So 0 is basically converted to minus 1 with some probability. I keep, by the way, if you start with totally random with half down and half up, it does, in fact it takes huge amount of time to reach a steady state. So you always put some bias, that is what I found. Okay. So you can do some your own fine tuning. So energy, so it is nearest neighbor node, so there are 4 neighbors. So you just take this whole system, shift it, shift left, shift right, shift up, shift down, and sum. Okay. So you can see that this is what this is, the shift left, no, 1 to n plus 1 is shifted left. So this is energy, and this is a loop. Okay. So if absolute m is less than, so I am putting this either it is goes to 0 or goes to 1, and is less than max steps, otherwise it will keep going, you know. So I will make a stopper number of steps. So you pick the site I j and flip its spin. I just putting minus 1 there. So minus 1 is flip, right. So minus 1 will go to plus 1 and 1 will go to minus 1. Then compute the energy, next energy, and so D is this E next minus E now, and so this is a, if energy is less than, okay, I am just doing it here. So so this is a, if I check, take a random number, if random number less than e power minus, so there should be one if, no, D, so except change. Okay, so I think even the lower energy is included in this. So this way I go to lower energy or higher energy, but with this probability I implement that algorithm, and then I loop it again. So this part is not extremely clear to me right now, but this is this should work also when E next is lower than E now. Okay, if E next is lower than E now, then this becomes, okay, I need to check. Okay, so this is supposedly taking care of both, but I need to check. Okay, so anyway, this is a Metropolis implementation. It's pretty simple, and what I got is this. I made 3 runs only, short of time, with a 100 by 100 grid. So so the critical temperature is this. It has been derived by Ising, not sorry, Ansager. Ansager solved this problem. You might have heard of this grid guy, no, Ansager. So he solved this problem and he computed the critical temperature to be normalized critical temperature. Okay, so kBT by J is Tc at T bar. So it should be dimensionless. Okay, so it's great to consider a dimensionless number. So critical temperature is 2.26918. This formula log 2 by log 1 plus root 2. So for T bar equal to 1, we should get the disordered state. Sorry, T bar equal to 1 should get a ordered state, lower than critical temperature. Yes or no? 1 and 2 I get ordered state. This is ordered state. Magnetization is 1. But for T bar equal to 10, I get a disordered state. I start with 0.7, is a biased. If you start with 0.5, then it takes long time. Okay. I want you to try to go as close as possible to this. But there are issues. When your temperature is close to critical temperature, then it is called critical slowing down. So its approach to equilibrium is very, very slow. So if you choose something like 2.1, or 2.2, it should go to ordered state, but it will go there very slowly. So, you need more steps, that is what it means. So, 2.28 and 2.27 and 2.26, these are pretty lengthy simulations, long ones, and that is what you should try. Okay, you should really show that for 2.6 is going to go to ordered and 2.7 is not. And well, we try with bigger grids. Okay, bigger grids may help. So, these are the issues. So, again I think GPU is great for this. You should use a single GPU. You can run with multi-core, but it is not going to be as fast. But yeah, so anyway, you try various options and choose the best option. Okay, so I will stop here.